last, for lunch, but definitely not least, a small startup that we just brought in to the university. I don't know if you've heard of it. It's Nvidia. No, but we've actually been working with Nvidia for a bit, and I'm pleased to have Nikhil Rao up to give a quick overview of what some of that looks like. Thanks a lot, Nikhil.
Thanks, Greg. I see a lot of hungry faces. I don't want to be in the way of food, so I'll try to keep this on time. So I thought I could not add much to what is already known to NVIDIA. So I thought for this talk, I'll kind of keep it to a topic which is sort of emerging in terms of how we train perception models and some of the AI for mobility, and also some of the toolkits that are developed by NVIDIA, and also how it applies to MCT and how MCT becomes a natural choice for some of the ideas which are emerging here to come to life. Particularly, if we look at the old playbook of modular perception, so we had all these data, all these sensors, camera, LiDAR, maps, rules, which were feeding into individual models, for detect cars, lanes, people, track, and also classification. This made sense back then when data was limited and whatnot. But if you take a closer look at these systems, any small change in one of the domains of operating of these models will multiply the maintainability cost across the whole stack of systems. So switch to today on foundation models. I know Dr. Liu touched on it a little bit earlier. You essentially have a reusable backbone of sorts where you feed in all of the data and it comes with a pre-trained starting point for all of your specific models. Say you have objects or segment scenes. These foundation models already come with a certain capability built in, and the whole idea is to adapt these foundation models to your specific use cases to squeeze out that last bit of performance. At this point, I want to kind of set the stage here to differentiate between three types of models. One is a vision foundation model that I kind of just talked about, where it is understanding visual patterns for detection and whatnot downstream tasks. The second is the vision language model, which is called the VLM, which interfaces language to vision, which enables us to have tasks where it can do question answering, summaries, labels, and of those sorts. The third is the world foundation models. Think of these models as physical models where they essentially reason about the next state of the world, what a particular action is going to produce. So that makes most sense for autonomous driving, where Alpamayo is one great example of that. All three make sense for MCT, but I want to focus on the vision foundation model and the language model on today's talk because I work on a team which builds a toolkit to fine-tune these models specifically. Going back to GTC, which happened in March, I think in addition to bigger models, much more larger GPUs, there was an overarching message of a shift towards physical AI. What this also means is that NVIDIA is kind of openly providing the entire stack of these solutions for different things, starting from model families with the Cosmos and the Alpamayos, to data factories where you have capabilities to curate your own data, multiply, and also validate. Third one is fine-tuning, where TAO comes in. We call it TAO, which stands for Train, Adapt, and Optimize, which I'm going to talk about today. Essentially, it gives you the capability to fine-tune all of these vision foundation models or VLMs to your own domain and have them work in your particular domain. The fourth one is simulation. I think there's a lot of work which is already being done in that front with the Omniverse and some of the digital twins things. So the idea here is that a lot of the real world data you're able to multiply, even in terms of the volume of data, the kind of um, uh, coverage of data, as well as multiply the amount of capability from these models. So what is NVIDIA TAO? So it essentially is a customization loop which the toolkit provides. You start with a foundation model, bring your own local data, um, very lightweight fine tuning which goes into your local data to adapt to your local circumstances. Optimize for edge. I think this is a good this is a very good candidate to optimize for edge because it has support for quantization, a lot of interface to TensorRT engines and all of these. So which really enables you to go to the edge pretty easily. You deploy and monitor, as well as feedback and sort of bring that loop together. So what this could mean for Mcity, right? So Mcity, I think we have a lot of rare crossing events, some of the construction zones, and all of these. The models, which are the VLM models, can really use some of this data to adapt to these particular circumstances and really enhance in performance in that sense. A practical example I put there was a fleet video search. Even there, I think these models can come in handy where you want to find particular scenarios pretty quickly about if you're training other traditional models to see for among video search and summarization, and also sensor variations and see how it can improve these models. So, what does this change in practice? Um, the whole shift from traditional stack where we had individual models to wild foundation models as well as fine tuning is that we're not here, you know, going for a flashier model. We want to adapt these models to our own particular use case and have them be deployable. So from the data point, you have manual labels, which goes to auto labeling, curation, and focus labeling. And models from many, like I alluded to before, many tasks to shared foundations with custom, very lightweight custom heads with LoRa. On the deployment side of things, you have research checkpoints to actually optimized to the edge solutions, which take your models to the edge. I guess the takeaway is customize the model to the place, particularly with how foundation models are coming about. Thank you.